In this lecture, we're going to continue our discussion on thermodynamics of continuous media. In the previous lecture, we have left discussing the first law on the axiom of thermodynamics. To recapitulate some of the idea, we begin with the notion of power, which is denoted by P, nothing but the energy delivered, rate of the energy delivered. So the power can be categorized into two broadly categorized into two items, that is mechanical part, and another one is the thermal part. So the power of the continuous body, if we have a axis which is x1, x2, and x3, and this the body B, if we consider a batch area, this is the unit normal acting in the direction, and this is the traction field. And another stress field inside the body is B. This is the origin B and the boundary is del B. So the power, that is mechanical power transferred, is integration of rho B dot B dB plus traction field T traction field T dot B ds. This mechanical energy that is being delivered will cause change in kinetic energy of rho B squared del B plus the stress transferred to the body, that is rho contracted with D dV. All of this is discussed in the previous video. So PE categorized in two terms, that is the change in kinetic energy, the rate of change of stress power. We'll box around it. Moving on to the next topic, we have stress power. So stress power, to summarize, stress power, it is the mechanical power entering into the system which is not spent in changing the kinetic energy. The part that is not change, that does not contribute to change in kinetic energy. So the power input is the mechanical input and the thermal input. Mechanical input, we have seen, is one part is responsible to contribute in change in kinetic energy. Another part is mechanical stress power. This is the stress tensor, and this is the symmetric part of the deformation gradient. And the thermal part is, this R is the heat producing field inside the body per unit of volume, dV, plus this is the Fourier-Stokes the flux vector dot with the unit normal of the surface n, ds. The energy, this is the expression for energy input into the body. Now, stored mechanical energy. Stored mechanical energy. Stored mechanical energy, the energy that is stored is the kinetic energy. Why kinetic energy? Um, Imagine a bullet that is speeding towards a blank and it penetrates the blank. The part of the kinetic energy can be converted into the heat energy. So this kinetic part is the recoverable part. Rho v square dv plus the change in the free energy. Free energy is the part that can be extracted from the body. So it is the rate of change of kinetic energy and the rate of change of free energy. We bring a notion, rho zero psi, called it the density of free energy. The stored energy per unit of volume. As we have discussed the stored energy, what we have to yet to discuss is dissipation. First, let's discuss about mechanical dissipation. Mechanical dissipation, suppose this is a body and we input some mechanical energy. We can decompose it into two parts. In one part, we have the energy that is stored and the energy that is lost. This is the dissipation. We denote it by D, dissipation, and mechanical MCH stands for mechanical energy, PE minus P stored. So my PE is dk dt plus sigma contracted with deformation gradient, symmetric part of the deformation gradient, minus P stored. P stored is dk dt minus integration of rho psi dot dv. This two cancels out. So dmax is equals to rho contracted with d minus rho psi dot d. This is only the mechanical part. We have a thermal dissipation. What is thermal dissipation? If you remember that thermal dissipation is equals to dq over temperature T. So dq equals to T ds. If we take the rate, we have the rate of dissipation, q dot equals to d dot s, keeping the entropy at fixed. For a fixed entropy, this is the rate of change of dissipation. So for a continuous body, expression becomes rho, entropy per unit volume, rate of temperature, dV over V. So this part is thermal um, dissipation. Now the total dissipation is the thermal and the mechanical. The thermal part, we have seen that it is rho, sigma contracted with the symmetric part of the deformation gradient minus rho psi dot, and the mechanical part is rho psi that dot. So sorry, we have this is this part. This part here is the mechanical part, and this part here, the thermal part. Now we have to integrate it over. We have to integrate it over the entire volume dV. This expression true for all delta V, small volume V, that belongs to V. This expression that D is rho contracted with D, that's rho psi dot plus psi dot plus, sorry, it is not psi, it is the entropy per unit volume, S. So it is S theta dot dV. It has to be greater than equal to 0. Pointwise form, we can write D minus rho psi dot plus S theta dot greater than equal to 0. This expression on the left hand side is called dissipation density, density of dissipation or dissipation density. This is the second law, or the Clausius-Planck or Clausius-Durham inequality in terms of free energy. We have another form of this equation in terms of internal energy or specific internal energy U, which is the internal energy per unit of mass, is basically the free energy or the energy extracted from the system plus S theta, this is thermal stored energy. This is the mechanical stored energy, MECH, stored energy, and this the thermal stored energy, and it is the total stored energy. You take the derivative, we end up with psi dot plus S theta dot plus S dot theta. We need the expression for psi dot plus S theta dot, which is U dot minus theta S dot. Our expression for second law was like this: psi dot plus S theta dot greater than equal to 0. So in terms of our internal energy, for this expression in the bracket, we can write U dot minus theta S dot, theta S dot, 0. Both are the form of second law of thermodynamics. For small strain deformation, our D is deformation gradient D is the rate of strain tensor. The second law becomes this. This is the second law for infinitesimal deformation. That's all for today.